All right. So in this video, we're going to talk through the answers to the timed FRQ option number 2. And yeah, so if you look at this first one, 1A, we're trying to figure out the oxidation number of chlorine in sodium chloride. So I'm going to look at my rules for determining my oxidation number. And let me see if I can get my pen to work. Okay, here we go. And so if we think about some of our rules for oxidation numbers, well, first of all, if I look at this looks like an ionic compound. And I can say that because I know I've got at least one metal and non-metal in there. And so I can recognize that this right here, this is the sodium ion. And the oxidation number is the same as the charge when you have a monoatomic ion. And then here, in this polyatomic ion, these charges add up to -1. I know that if you look at your oxidation number rules, we say that oxygen usually has an oxidation number of -2, and unless it's a peroxide, and then, or unless if it's on its own. If it was, molecular oxygen, it would have an oxidation number of 0. If it were in hydrogen peroxide, oxygen has an oxidation of -1. But otherwise, in a compounds, it typically has a -2 oxidation number. And then by kind of process of elimination, I can figure out what your chlorine must be. So this one must be +1 here. So the oxidation number of chlorine is +1. And we calculate the number of grams of sodium thiosulfate needed to prepare 100 milliliters of 0.5 molar. So this is just a solutions calculation problem. So in order to find grams, I'm first going to find moles, and then I'm going to convert moles to grams. So I'm going to find moles by doing my molarity times my volume. So it's 0.5 molar times my volume, which is this number technically has 1, 2, 3, 4, 5 sig figs in it. This number has 3 sig figs in it. So my answer is going to have 3 sig figs in it, so 0.05 moles. And then that's step 1. Then I'm going to take my moles and I'm going to convert it to grams using the molar mass of sodium thiosulfate. Okay, so let's take a look at some sample responses, and we can see what our numerical answer should be here. So in this first one, your oxidation number is +1. And notice for A, they didn't ask you to provide reasoning. Typically on oxidation number problems, you just have to give the oxidation number. You don't have to explain your work unless they ask you for it. If they ask you to explain your work, then make sure you justify it. But in this case, they said, what's the oxidation number? So all you gotta do is do +1. And then the second part, we have moles, and then we go from moles to grams at 7.91 grams. So your answer should have 3 sig figs in it. And here's an example of how you would show it typed. Notice how with here, the way you'd show the subscripts is you just don't even worry about the fact they're subscripts. So don't bother spending your time trying to figure out how to type in subscripts. You can just write it this way, Na2S2O3. They put that in the keyboarding guidelines as an example of how you should type it. So our scoring guidelines, again, for A, you get 1 point for +1. And then for part B, this was actually a 2-pointer. So you never know when a question is going to be worth multiple points. It could be a 1-pointer, it could be a 2-pointer, it could even be a 3-pointer sometimes for one of these parts of a question. In this case, you got 2 points, 1 point for finding moles correctly, and then 1 point for finding the correct mass, consistent with your number of moles. This is key here. So let's say you messed up on this first part and you found moles wrong. If you did the second part correctly based on what you said for the first part, you would still earn the credit here. So if you said, oh, there's 500 moles, and then you took 500 times 158 to find your mass, you would still earn this second point here for finding the mass correctly. So that's key. So if you're not sure how to do part of a problem, then just kind of do your best and kind of make a guess. And then you can if you use that number correctly later on in a later part of a problem, you can still earn those later points. So that's really important to think about. So if you look at C, we're trying to figure out who is the limiting reactant, and we want to justify our answer here. And I don't have my balanced chemical equation on this page. I kind of need to look at my balanced chemical equation to figure this out. But one thing I will notice from glancing at this first is that to find my limiting reactant, I first need to figure out how many moles of each reactant that we have. And since in this case these are all aqueous reactants, they're solutions. To find moles, we take the molarity times the volume. And what we should notice here is that they all have the same number of moles. So you've got the same number of moles of all three of your reactants. A word you can use here for this if you want to, you can call them equimolar. We have equimolar amounts of each of our three reactants. And then we need to look at our balanced chemical equation. So I'm going to flip back here to this screen. If you look here, we have equimolar amounts, but it looks like we need, for every one of these that reacts, we need 4 of these and 2 of these. So we need more of sodium hypochlorite than the other 2 reactants. So one way in which we could answer this question here is actually without doing much math. We could just say, let me flip to this answer. You could say this response: because all solutions have equal molar amounts, but in the reaction you only need 1 Na2SO3 compared to 4 NaOCls and 1 NaOH, therefore your limiting reactant is NaOCl. So you could kind of give a response that works here without doing any real calculations. If you look at the scoring guidelines, that is the method they show in the scoring guidelines. They say NaOCl is the limiting reactant. Given that there are equal number of moles of each reactant, it follows from the coefficients in the balanced equation that NaOCl will be depleted first. So basically the limiting reactant is the thing that you're going to run out of first, and so it's going to limit how much product you make. And notice how this is just a 1-pointer. So you get 1 point for providing the limiting reactant and providing a valid justification. So if all you did is write down NaOCl and did not have a justification, you would earn 0 points in this question. The other way of doing this, so I'm kind of going backwards here, is to do a calculation. And so this is how we typically talk about limiting reactants, is we figure out how many moles of reactant you have, and then you pick a product. And you can figure out, like in this context, in this example, they use the idea of moles reaction. So basically for every 1 reaction that you have, you use up 1 Na2SO4, but 4 NaOCls and 2 NaOHs. So notice how the NaOCl makes the smallest number, and that's why it's our limiting reactant. So it's another way to think about it mathematically. There, what's going on here. And then in this case, we figured out how much product it would form. And if you look at the chemical reaction, Na2SO4 was one of your products. So one way to calculate and figure out what's the limiting reactant is you ask yourself, if I used up all of this reactant, how much product would I make? And same thing for this one, how much product would I make? And same thing for this one. And whoever makes the least amount of product is going to be your limiting reactant. So these are all 3 valid ways of answering this question, and they would all earn that 1 point there. Okay. So if we look at this one, D is just doing some graphical interpretation. What is the temperature change? And then you're going to use that temperature change to calculate the energy that is released there. So for the temperature change, this is kind of graphical interpretation. So can you read a graph and interpret initial and final temperatures? You should find that the temperature change is 12.5 degrees Celsius. This is the type of question that you might be assessed for sig figs on. And so you're just looking at this one, you're saying, oh, this looks like it's about, 32.5, and this one right here is 20. So you're just looking at your, temperature change there. And then we are trying to find the heat energy. So you're trying to solve for heat, and we've got measuring some temperature. That tells us, hey, we should be using this equation right here, Q equals MC delta T. And the mass, and some of these problems, the tricky part about MC delta T is determining the mass correctly. Like, should I combine the masses together or do they stay separate? What's going on in the context? In this problem, they make it pretty clear that the entire reaction mixture is 15.21 grams. So they made picking the mass easy for you because they only give you one option there. And then the specific heat is 3.94 joules per gram degree Celsius. And the change in temperature was 12.5 degrees Celsius. Notice that my answer should have 3 sig figs in it, because these values both have 3 sig figs. This one has 4 sig figs. So I'm going to go with the one with the fewest sig figs. So our answer should be 749 joules. And in this question, I don't think they specified, oh no, they did specify you should report it in joules. So you want to make sure you report this in joules. So 749 would be the way to go here. The scoring guidelines, the temperature change was 1 point, and then E was a 1-pointer. Sometimes an MCAT calculation will be a 2-pointer. It kind of depends on how much stuff you have to figure out, but notice how they already gave you a point up here for finding the temperature, and they told you what the mass was. So really you're just kind of plugging in these numbers. So that was just a 1-point calculation in this context. This part was the most commonly missed based on the responses that I've seen, so double I, and which is not surprising because it's a little bit tricky with the mole reaction concept here. So using the balanced chemical equation and your answer to part C, which I just repasted right here, we're going to calculate the value of the enthalpy change of the reaction in energy per mole reaction, include the appropriate algebraic sign. They give you a little hint here to think about sign. So it's always important to think about sign and units here. So one thing you want to keep in mind is if you think about what's happening here in the system here, you have this reaction, and then when you're doing calorimetry, you're measuring the surroundings. So the surroundings increased in temperature. That means the reaction released energy. So basically the surroundings, we saw the temperature went up. So that means they gained energy. They gained 749 joules of energy. That tells you that the reaction gave off 749 joules of energy. So it looks like this reaction is exothermic. And we can tell that because the surrounding temp increased. And we want to report it in kilojoules per mole reaction. So I'm going to convert my joules to kilojoules. So that's 0.749 kilojoules. And then I want to find moles reaction. So right now I need to go back and take a look at my data from earlier, and consider who my limiting reactant is. So this reaction has 3 reactants in it. So whenever we're trying to find the energy per mole, first I want to use the limiting reactant. And then I want to convert moles of reactant into moles reaction. And if we look back at your previous answer and you identify your limiting reactant, we found that the limiting reactant was sodium hypochlorite. And that was in the answer to, let me look back, that was the answer to part C. Oh, and that's what they referred to here. Part C, that was our limiting reactant there. And if you think about how much NaOCl reacted, it was you had 0.05 liters, and the molarity was 0.5 molar, and so we had 0.0025 moles of your limiting reactant. Okay. Then I want to take this number, I want to convert it into moles reaction. And the idea behind a mole reaction is to think of this thing right here as a kind of unit in itself. So in 1 mole of reaction, we have 1 mole of sodium NaS2O3, and then we have 4 moles of NaOCl, and we have 2 moles of NaOH react. So you can think of this as kind of its own set of mole ratios here. 1 mole of reaction is 1 mole of this, 4 moles of this, and 2 moles of this. So what I want to do here is I want to take my limiting reactant, 0.025 moles of NaOCl, and I want to convert moles of NaOCl to moles of reaction. So in every one of these reactions up here, I use up 4 moles of NaOCl. So the moles of reaction is 0.000625. So it's a quarter of what my limiting reactant is. So then to find, excuse me, the delta H, I would take my kilojoules value here and divide it by my moles reaction, and then that is going to give me negative 1.20 times 10 to the third, which is, 1, 2, 3 kilojoules per mole. I think the reason why we wrote it this way is actually, this is one of those cases where to report it with 3 sig figs, you actually have to use scientific notation. If I were to write it this way, my value would only have 2 sig figs in it. So you actually have to use scientific notation in this case. So this is a tricky one, all sorts of things happening here. Let's take a look at some sample responses here. Well, here's the scoring guidelines. So you get a point for correctly calculating the mole reaction consistent with the limiting reactant in part C. So if you chose the wrong limiting reactant in part C, but you did this part correct based on your answer to part C, you would still earn the full points here. And then you get a point for having a negative delta H that you got by taking your energy and dividing it by the moles reaction. So again, even if you messed up on this part here, you could still get this point correct for recognizing that it is exothermic, putting a negative in front of it, and by taking your energy and dividing it by whatever moles you figured out. Okay, so if we look at an example here, if you look at this response that's typed, it looks like our numerical answer is not correct in the end, and that was because we kind of missed the mole ratio. We got the right idea here. They want to convert moles NaOCl to moles reaction, but this should actually have been a 4 there. But you would still get, 1 point here for taking this value and dividing it by the moles reaction that you found. So you'd still earn a point for this problem. And then this problem, initially, when you look at it, it looks like it might be incorrect because the number doesn't match our previous answer. But in this case, the person had identified this as the limiting reactant from part C. So you actually would have earned full points on this one because they correctly used the answer from part C to find the answer to this problem. Okay, so let's take a look at this one. If we're looking at F, oh yeah, sorry, remember what the question is. So if you're looking at F, if you compare this to the original data table, what's different here is we doubled all the volumes. And what they're saying is if we do this experiment, when we double all the volumes, we end up with the same delta H. And the reason why, so I want to explain this result. So remember, delta H is a ratio, energy per moles reaction. So what happens here is when you double the volumes, you are going to end up releasing twice as much energy. So your calculated energy value is going to be bigger, but you're also reacting twice as many moles. So since it's a ratio, if you double the energy and you also double the moles, you're going to end up with the same ratio as in that first experiment. So let's look at an example here of some responses. So increasing the volume of reactants also increases the reaction proportionally, so the same amount of energy is transferred per 1 mole of reaction. And then here's part of an excerpt of a response. I want to show this visual. They had a written response as well, but I kind of like this visual. I thought it was helpful. You're increasing the energy, and you're also increasing the moles by the same amount, so you have the same delta H ratio. And here's an example down here, which is kind of similar to what I was drawing out on the previous page. You're doubling the heat release, but you're also doubling moles, so the ratio ends up being the same in these two reactions. And here's an example of how they wrote it out in words. So by doubling the volumes, number of moles are doubled, doubles the energy produced, but the energy per mole remains the same. So that was a one-pointer. They're looking for a valid explanation. You can do it mathematically or describing it in words. And then the second part of it was let me go back to the question here. The second part is write a balanced net ionic equation for the given reaction. So in this case, the reaction is already given up here at the top of the problem, and it's given in its molecular form. So the key thing here is there's two things you want to do. First, you want to ionize any aqueous, ionic, or acids. So anything that's an aqueous compound that's an ionic or an acid, you're going to ionize it. And then the second thing you want to do is eliminate spectators. And the most common mistake I see in this type of problem is over-ionizing things. Okay, so like for example, water. Water is not an aqueous ionic compound or an acid, so don't ionize it. Leave it as water. Okay, and then sodium chloride is ionic. I'm going to split it apart, and aqueous. I'm going to split it apart into its ions. And then right here, this is an ionic compound. I can recognize that because I've got, you know, metals and nonmetals. And I break it up into ions. I'm only going to make 2 ions. So SO4 sulfate is a polyatomic ion. So those S's and O's, they stick together. You don't want to break them down any further than that. So, and even if you have a polyatomic ion that is unfamiliar to you, like let's say over here, this is thiosulfate. It wasn't on the list of polyatomic ions that we memorized, but you can look at this and say, okay, it's an ionic compound. I know ionic compounds are always made up of 2 ions. This ion I recognize, okay, I've got 2 sodium ions. I know that sodium ions have a +1 charge. So therefore, I can figure out that this thing, S2O3, must have a -2 charge. So you can figure out that this is S2O3 with a charge of -2 without having like memorized S2O3 as on your list of polyatomic ions. So just kind of figure it out from eliminations. Like in this case, it looks like I have 4 sodium ions. And then this thing over here, what's left, that must be a polyatomic ion. It must have a charge of -1 because there's 1 of these for every 1 sodium. And yeah, so just kind of figure it out that way. So when you ionize these, it should end up looking something like this. So here's one where I kind of wrote it out with the, this is what we call the complete ionic equation, where we ionize the things and looked for spectators. And you don't have to write out the complete ionic equation. Notice in the scoring guideline, all they did was show the final answer. This is the correct net ionic equation. But if doing this work helps you, like, you know, it might help you to kind of write this out there. And the common mistake is to, again, overdo the ionizing. So like breaking apart polyatomic ions or breaking apart water. So this is an example of that, kind of over-ionizing things. So make sure your polyatomics stay intact, like SO4, S2O3. And again, you can figure out your charge of your polyatomic based on what it's bonded to. Okay. Oh, I lost my go ahead thing. Okay, here we go. There we go, screen. Okay. So the last part, we're looking at a photoelectron spectrum here, and we're trying to identify the element. And notice how I don't have to justify my answer. I'm just identify the element. So I see that there are 3 peaks, and we know that each peak corresponds to a location where there are electrons, or where the electrons are, I should phrase it that way. And this is a photoelectron spectra. We talked about this in Unit 1. And notice how this is a high energy peak, and these ones over here are lower energy. So the higher energy ones are the ones that are going to be closer to the nucleus. So this highest energy peak is going to correspond to that closest location where the electrons can be, which is the 1s subshell. And then this one is going to be the next highest, so it's 2s, and this one's going to be the next closest. So it looks like we have something with 1s, 2s, and 2p. And then we can look at these numbers. I know that the most electrons we can fit in an s orbital is 2. So now based on this scale, I can figure out that each of these lines seems to represent 1 electron. So this 2s must also have 2 electrons in it. And then this one looks like it's 3 high, so this is 2p3. So we are looking at this electron configuration and using that to identify what the element is, and that is nitrogen. So again, this problem, they didn't ask for an explanation. All you had to say is, it's nitrogen, and you earn that 1 point. And then calculate the value of the rate constant. So whenever you see half-life, then you can go back and take a look at that half-life equation, which is on your equation sheet, that the half-life is 0.693 divided by K, or you can rearrange it where K is 0.693 divided by your half-life. I can't remember which way it shows up on your equation sheet. So we're going to solve for K. Sorry, I'm looking back at my notes here. Yeah, this is the way it shows up on your equation sheet, but we're going to rearrange it like this. And that top value is a unitless number. The reason why this is unitless is because it's based on that first order integrated rate law where you take the natural log of some numbers, and remember, log values are always unitless. So this number is unitless. Okay, so we're going to take 0.693 divided by the half-life, which is 10 minutes. And there's a dot there. That means that that 0 is significant. And so you just take 0.693 divided by 10, which is 0.0693. Although really we should write as 0.069 because I only have 2 sig figs here. And then the units are 1 over minutes. Or we could write that as minutes to the negative 1. Whoops, I wrote that the wrong way. Minutes to the negative 1. Okay. So here's some examples here. If we look right here at this example, and then this example right here, we can see the most common mistake, and this is true for really for these rate constant calculations in general, is the most common mistake is with the units. So just be really careful with the units. So these answers, they both left the units off. It turns out this question was a 2-point question. You got a point for the correct answer and a point for the correct units. So in these examples, we would have earned 1 point out of the 2 possible. Okay, this one would have earned both points because we've got the correct value and the units. And then the second part of the question said, how long would it take to go from 64 atoms to 1 atom? So in these 3 examples, they all use the same kind of strategy, using the idea that the half-life is the amount of time it takes for half of your sample to decay. So we just cut it in half and half and half and half and half and half again until we finally get to only 1 atom left over. And then you just kind of add up, well, how long did that take? It took 60 minutes. So the other option for doing this, just so you know, is you could also use the integrated rate law. And then you could plug in the values. You could say at the end we're going to have 1 atom. We start out with 64. Plug in the value of K that you figured out in part B, and then you can solve it that way as well. So let me know if you have any follow-up questions. I think that's the end here of our notes. Hope that was helpful.